Okay, so in the last video I talked about the property of normality when n goes to infinity, and I said that this property is essential to make statistical inferences so that we can use f-test and t-test, because if our random variable is normal, then 95% of the observations will lie within 2 standard deviations of the mean value. In this video, I'm going to talk about the variance of beta j, and we already know that we estimate this variance using this formula, where this is the estimated value of sigma squared from our regression model. SST j is the sum of square total of our variable xj, and r squared j, it is the r squared that we get from regressing our variable of interest xj on all other variables. And as n goes to infinity, we're going to see that the variance of beta j get closer and closer to 0 at the rate of 1 over n. And this implies that the standard error of beta j will go towards 0 at the rate of 1 over the square root of n. And this is what I'm going to show you using an example. Okay, so birth weight is our dependent variable, which shows birth weight in pound. Then the second variable, cigarettes, it shows the average number of cigarettes the mother smoked per day during the pregnancy. And our second variable, parity, it shows the birth order of the child. And this variable, family income, it shows the annual family income. And finally, these two final variables, mother education and father education, show years of schooling for the father and the mother. And we are interested in exploring the relationship between birth weight and all these characteristics. So the first thing I'm going to do is I'm going to split my sample and regress this variable only on the first half of the observations. And doing this, my standard error of cigarette is 0.0013. And next, I'm going to regress birth weight on the whole sample. So let's call this small, and our large sample is giving us standard error of cigarettes as 0.00086. So we can calculate the ratio between these two as 0.000, and this ratio is approximately 0.662 or 66.2%. Next, we are going to obtain the ratios between the number of observations in the small sample and the number of observations in the large sample. And we're going to take the square root of this ratio, because there are 694 observations in the small data and 1,388 observations in the larger sample. And this gives us 0.707 or 70.7%. So what this means is that standard error using the large sample should be about 70.7% of the standard error using the small sample. So it seems like a larger sample is giving us smaller standard error. And remember, this is what we want. So a large sample is better. We saw that the ratio between the standard errors of a small sample and a large sample is about 66.2%, which is very close to the 70%. So this proves that a larger sample gives us a variance smaller than a small sample. As we saw in this case, that a larger sample is giving us a standard error which is about 66% of the smaller sample. Alright, see you in the next video. Bye bye.